Okay, hi everyone. Welcome to our ANC seminar, our second ANC seminar of the year. And today we're very happy and excited to have Vishwas to come and talk to us about A Tale of Two Reconstructions. Vishwas is a fifth-year PhD at Rutgers, and he has done like amazing work in factoring and reconstruction, and apparently now like fast multi-point evaluation, as far as I know, with wonderful collaborators as well. And also just breaking news, right? So I'm very excited that Vishwas will be joining us in Waterloo in the fall as one of the prestigious postdoc fellows. So yeah, welcome to Waterloo, Vishwas, and take it away.
Okay. Yeah, thank you for the introduction. So again, I'm also very excited to join Waterloo in the fall. So I'll hopefully be able to demonstrate what kind of work I do with this talk. So I'll be talking about a tale of two reconstruction. So since it's a tale, it will be more of a survey than about a particular result. I somehow feel like if my title is A Tale of Two Reconstructions, I have to start by it was the best of times and worst of times. So it's kind of true in the following sense, because if you see these reconstruction results, you will see the best of times being a paper titled, oh, we can learn random circuits, we can run random formulas. And also the worst of time, because you'll see a paper with 50-page long, extremely intricate maths, which deals with depth 3 circuits with top fan in 2. So this talk is kind of giving an explanation how things get complicated in one part of learning and not that much in the other part. So again, I'll be talking about average case and worst case reconstruction. I'll elaborate everything in the talk. So okay, I'll start. So again, the reconstruction problems is in the arithmetic circuit setting. Here, the model is called arithmetic circuits, which compute polynomials. So these are nothing but the directed acyclic graphs where internal nodes have addition and multiplication gates, leaves have variables or field constants, and edges have field constants. So, for example, this is an example of an arithmetic circuit. These are multiplication addition gates, and these are symbolic variables. You can have some constants here, like 2, 3, and so on. And the output would be a polynomial. So as it turns out, you can actually layer your addition and multiplication gates alternatively. So for instance, you can have a sigma layer followed by a pi layer followed by sigma layer. It will be relevant for the talk to have a notion of depth of a circuit. So depth of a circuit is the same depth of this DAG. So here the depth is depth 3. So if you look at this polynomial, this circuit, it computes sums of products of linear forms. So it will compute circuits which look something like this. So you have a bunch of linear forms, L2, L2, L3, and then L1 prime, L2 prime, L3 prime, and so on. Okay, so this is the introduction to arithmetic circuits. Now the problem of reconstruction. So it's a very fundamental problem in the field. Here you're hidden the circuit from yourself, and you are only given the black box access to the polynomial, which means you can give the black box any point and the black box will give you an evaluation. Along with that, you're given a promise that, oh, this polynomial that you're given has a small circuit, and this could be of a particular class. For, let's say, it has a depth 3 circuit or something particular. What you want to output is an arithmetic circuit computing F, and if your output circuit turns out to be of the same class from which the input was promised, then it's called proper learning, otherwise improper learning. So in this talk, we'll be only be focusing on proper learning. Okay, so the first thing is that this problem is extremely hard for most circuit classes. So I'll give a bunch of reasons why is the case. So first is that uh, learning implies lower bounds. So this is a result by Fortnow and Clevans in 2009, which says if you can reconstruct a circuit class, it can be a randomized algorithm or a deterministic algorithm, then you will get a super polynomial lower bound against that circuit class, and the explicit polynomial would be some BPX explicit. Anyway, so the moral of this result is you should only try to do reconstruction once you have lower bounds. If you don't have lower bounds, it's a harder problem to do reconstruction. So that's one reason, because lower bound is so hard to get. So that's another reason why reconstruction should be hard as well. There are some NP hardness results. These are essentially what we get out of hardness of tensor decomposition. So we know that by Hausdorff result, the tensor decomposition is NP hard. From that, we get two immediate corollaries. So that reconstructing optimal size depth 3 set multilinear circuit. Again, this notion is not very important, the detail, but some kind of restricted circuit is NP hard to find the shortest representation. So it gives us an hardness result. And similarly for depth 3 powering circuits, so this amounts to computing the symmetric tensor, right? So let me just give a slight definition what depth 3 powering circuit is, because it will be relevant later in the talk. So these are, I'll be denoting them by some power sum, and they essentially compute polynomials which look like this: L1 to the D plus L2 to the D dot ls to the D. So it's sums of powers of linear function. Again, so finding the optimal decomposition of a polynomial like this is also NP hard due to the result by Shitov. There are some other hardness results as well. So there is some cryptographic hardness result that if you can pack learn depth 3 circuits, then you can get a quantum algorithm for lattice problems. And there's this basic analogy to MCSP problem, which is a similar problem in the Boolean setting, which is expected to be hard, NP hard in particular. So these are all the reasons that we have why we think reconstruction is important. I hope there will be much more concrete result, but right now we have just this much. Okay, but despite all these hardness results, there have been quite a bit of progress. So there are a lot of known results and special classes for which there are reconstruction algorithms known. So let's just focus on worst case learning. So what do I mean by worst case learning? So I'll just tell you that the polynomial comes from a circuit class, and on top of that, I will have no additional assumption. So this is what I refer as worst case learning. So the results we know here are sparse polynomial learning. That is, if you have just, let's say, polynomially many monomials. There's depth 3 circuits with, so this means the top panel. And when I use the term k, think of k as being constant, like 100. So if the top panel is constant, then depth 3 circuits can be learned over finite fields. This is a result by Karnin-Spilka. We later gave a result which works for all fields. This was joint work with Shubhangi and Ilya, which works for multilinear circuits and set multilinear circuits. So we improved this finite fields dependent to all fields, but we have to have this extra assumption of multilinearity. We also generalized this to depth 4 circuit in a previous work, but with the finite field restrictions. There are some results which are known for top fan 2 circuits. You can think of it as like the first non-trivial case that you encounter in learning. And then there's this class of ROABPs, which has very nice structure, so we can learn it quite well. So these are all the worst.
Are all these proper learning?
Right. These are all proper learning.
Okay.
Right. So there is right. These are all proper learning. Right. So Karnin-Spilka is not. There is slight blow up in Karnin-Spilka, but
right. So Karnin-Spilka is not proper learning, right? Because
right. They define something called a generalized depth 3.
Right.
In these models, do you know what k is, or do you just know that?
So in this talk, when I write k, it means, let's say, order 1, which is 100, let's say, and when I write s, think of it like n to the 100. Like
okay.
K is constant. Right?
I see.
Right. Beyond constant of Fanon, it's very hard to get reconstructed. Also because of some NP hardness result, right? So set multilinear depth 3 is a subclass of depth 3. So we don't expect to get the reconstruction algorithm when K. You have to have some kind of assumption to surpass the NP hardness. All right. So these are all the results for worst case reconstruction, which are proper.
All right, yeah, and just to address the question that Abhi asked, like for the constant, you can always assume that, like, you know, an upper bound on k, maybe not necessarily k, but yeah, you can say, oh, I can assume that k is actually 100, and I can work with the 100 because you can always discover, like,
right. You can iteratively start by assuming case 1, case 2, and so on. So you will find the minimum representation. All right. So now moving on to average case learning. So average case learning here basically means that apart from the promise that the polynomial comes from a circuit class, there's some additional restrictions that I like conditions that I'll assume that my circuit has. We'll see a bunch of examples later. And those conditions I'll somehow show they hold for random circuits. So this is what we'll mean by average case learning. So there was previously these three results. These are like random fan into regular formulas by Gupta Kayal Locum and Gupta Kayal Kyao. And then there was full rank algebraic ABPs and low with ABPs. Again, all these three results were kind of very restrictive on the structure. But recently there has been some development which we refer to as non-degenerate learning. Here the restrictions on the circuit are very relaxed, so very minimal requirements are assumed, and so they're in some sense stronger average case learning, and these will be the focus of this talk. So basically in the non-degenerate case we can learn depth 3 circuits, we can learn sums of powers of low degree polynomials, and we can learn non-degenerate generalized depth 3. I'll elaborate on this later. So yeah, these are the results we know for average case learning. So again, to emphasize on my point, so what's going on?
Oh, sorry, yeah, Vishwas, right. Just if you go back, just for the audience, like when we mean non-degenerate here, like if you're in computer science, you can think that this is something that holds for a random circuit of that form. Okay, right, so non-degenerate here just means like there's this very special set of, you know, measure zero, if you will, that like it won't hold for those circuits. Yeah, just that.
Right. So the non-degenerate, so the degenerate circuits are actually very rare. They lie on some kind of variety. So most of the circuits will not be.
Right. And well, they're very rare, but in general, these are the circuits we're interested in. Right.
Right. So for the end, I'll show a very concrete example soon, where you will also see what kinds of non-degeneracy conditions one will encounter. Right. But as I mentioned, these conditions they hold for random circuits. So again, so as I discussed, there are two paradigms: average case and worst case. So is there any connection between their techniques? And again, so on average, we can learn formulas, and even in the worst case, depth 3 with top fan in 3 is a struggle. So what's going on over here? So let's try to understand this with a case study for the simplest model that we understand, that's sums of powers of linear forms. So we'll look at two algorithms, one being a non-degenerate algorithm and another worst case algorithm for this model. So we'll look at a non-degenerate algorithm. So this was by Kayal 2011, and then we'll look at a concept. So we'll look at, in the worst case, we look at sigma power sigma k, that is rank 10. So this I'm written in terms of tensors here because this actually turns out to be equivalent to learning. This turns out to be equivalent to decomposing a tensor, a symmetric tensor. All right. So basically, we'll look at for this model average as well as worst case algorithm now. Okay. So let's look at the non-degenerate algorithm for it. So again, what's our model? I've given a polynomial with L1 to the D plus L2 to the D dot dot. Let's assume for simplicity it's n. Okay. So let's try to analyze what happens when I differentiate this polynomial with, so del ij, by that I mean, so this is in n variables, x1 to xn. Del ij means essentially differentiating with respect to xi and xj. So what happens when you do this? So it's a linear operator, partial derivative. So I can just study it over 1 power of li. So if you look at this, summation k equal to 1 to n, because it's a linear operator.
So Vishwas, sorry, quick question. Are the two ends the same?
Right. Here it's the same. It doesn't really matter. I'm just making it for simplicity.
Okay.
Right. So this will be d minus 2 because you differentiate it twice. And what you'll get outside will be c ki and c kj. And what's cky, ckj? It's essentially, you think of lk being summation ckixi, and there will be a constant depending on d, which I'm ignoring. Right. So that's what comes out by taking the partial derivative. So if you interpret this as a matrix, right, I can interpret this as a matrix with entries, n cross n matrix, with entries being dou ij of f. And if you look at this expression carefully, think of it as a matrix product. So in matrix product, we usually look expression like this, b, k, j, things like that, right? So, but here it's together, but we can do a transpose to make it in this form. Essentially, if you stare at it long enough, you'll realize that there is a decomposition of this and this in the following form. So this matrix decomposes like this. Okay. So where the middle one is the diagonal L to d minus 2 dot ln to the d minus 2. Right. And this is essentially writing your li, say 2 to ln x1 xn, and this is its transpose. Okay, so let me elaborate. So this is basically the coefficient of x1 in L1 and so on. Okay, so this decomposition hold because of this identity. Very simply, since we know f, we have the information about partial derivative of f, so we know this matrix. So we know this matrix, and we would like to get our hands on this matrix, because if we have our hands on this matrix, we know LIs, and thus we know the representation. So we would like to learn this. So if you assume, so one way to do is to just look at determinant of this polynomial. If you look at determinant of this matrix, then if the determinant of this matrix and this matrix is non-zero, what you get, okay, let me just take this to the next page for simplicity. All right. So this is nothing but dou ij of f. So if you look at determinant of dou ij of the following matrix, so this is actually known as Hessian of the matrix of Hessian of f. It will give you some constant alpha times product of li to the d minus 2 nk. And if this alpha is non-zero, which is turns out to be the equivalent to this and this determinant being non-zero, which just turns out to be equivalent to if L1, L2 up to Ln are linearly independent. So basically, if Li's are linearly independent, you can just compute the determinant, factor it, and get your hands on all the Li's and simply learn the representation. So we can just call this a non-degeneracy condition. And one can note that if you sample n linear polynomials, they will be linearly independent with high probability. So by this very simple identity that the Hessian of a matrix of a polynomial factorizes like this, we get a non-degenerate learning algorithm for sums of powers of linear form. Any doubt in this? And it's actually very elementary. Okay, so I'll move on. So we saw. So this is, for example, one non-degeneracy condition. It holds for random polynomials. Again, it was very simple in this case because it's a very simple model. The non-degenerate condition gets really complicated when you go for depth 3 circuits or depth 4 circuits. Okay, now look at the worst case sum power sum decomposition. So assume f is L1 to the D, L2 to the D, dot L, let's say 10 to the D. Okay, how would you learn the following representation? So there is a result by Carlini. Okay, let before that. So it's a polynomial over n variables, sparse, but essentially it's just a polynomial over 10 variables. Why? Well, because you can always do a linear transformation and send this to, let's say, x1, x2 up to xn up to a linear transformation. So there's a result by Carlini which says that you can do this algorithmically very efficiently. So Carlini 06 said that there exists an efficient algorithm that finds A such that A is a matrix such that f of ax just depends on essential variables. So essential variables means you do a linear transformation, how much you can reduce the number of variables. Okay, so if we apply this transformation, now your polynomial f of ax L1 tilde to d dot L10 tilde to d. So if you can learn this transformation, you can just revert linear. If you learn this representation, you can just revert it to learn this one because you know A. How would you learn this representation? Well, this is a polynomial now over just 10 variables. So I will just, this is a sparse polynomial f of ax. So I'll learn this in the sparse representation. Look at the number of unknowns you know here. So since it depends on just 10 variables, you have 10 unknowns here, 10 unknowns here, and 10 unknowns here. So you have approximately 100 unknowns. And if you can, so if you write this up as a system of algebraic equation, it will just have 100 unknown variables. So there are known results if your system of equations have just constant number of variables unknowns, then you can brute force it to find a solution in polynomial time. So we just use that. So we use system solving. System solving. Okay, oh sorry. Let's say constant variate system solving. Okay. And any doubt in this? So basically, we did a simple transformation and did a brute force. Brute force means using the hammer of system solving for constant variable. Any doubt in this? Okay, so here we saw a worst case algorithm and an average case algorithm for the same model. Now I try to give a meta template for both of them and see how similar or different they are. So let me give a meta framework for learning in the non-degenerate case. So again, so our basic setting being f is sums of a bunch of polynomials. These polynomials are being easy polynomials. Think of f being a depth 3 circuit. In that case, the easy polynomials will be sums of will just be products of linear polynomials. All right. So right. So let me propose this meta framework. So our tool that we have at our disposal is vector space decomposition. To do that, we have to first convert our polynomial into a vector space. To do that, we apply some kinds of linear operator on the polynomial. So this is what we mean here. The first step is compute a basis of L of f from f. That is, look at the vector space. So one might ask, what is L? So L is actually the linear operator which usually we get from lower bound. So roughly you expect non-degenerate learning to happen only when you have lower bound for that model. For example, for depth 3, let's say homogeneous depth 3, we have lower bounds using partial derivative measure. So in that case, you can think of this linear operator to being just partial derivative operator. So linear operators, which are usually used from inspired from the lower bound. All right. So you compute up. So if you, for example, on depth circuit, if you apply the partial derivative, let's say kth order partial, that's a bunch of linear operator. It will give you a space. The space will be the, so this will be in that case would be the kth order partials on F. So this is space now, and you decompose this space, and you hope to learn from that decomposition your original simple polynomials, which will give you a. So this is a very, very rough meta framework. But
And
I guess,
here, I'm sorry, I think the key point here is that in step 2, you hope that this linear operator will decompose as a direct sum, right? Like that's your hope, because usually it is not a things can mix, right? But you're hoping that
right.
it's this linear operator preserves the independence of the TIs. Is that right?
Right. But even before that, there's a catch, because any vector space you can always decompose in terms of basis vectors, which will be a direct sum. So this meta framework is not very well formed, because again, this same reason I can always decompose into a direct sum. So how will you learn it? So this was the very crude one. So let's improve upon this. We somehow want some kind of uniqueness from our decomposition, because if there are, like, we apply the vector space decomposition algorithm, which is kind of our tool, it spits out something to us. If there's no uniqueness, you don't know what you learned, it came from the original representation. So anyway, there's no hope of uniqueness, because you can always decompose any vector space as a direct sum. We want to impose some extra condition. For that, we, instead of looking at a linear operator L, we look at a linear operator as a composition of two linear operators. So for example, standard example being kth order partials, if this is your L, I'll think of it as two-step process. I'll derivate it k minus 1 times. This is my L1, and then I derivate it once again. So this will be my L2, and so this will hold. Anyways, we want the following. We want that when I apply the k minus 1 order partials on F, there is a decomposition, and there is another decomposition that you can decompose L of F such that it's each component you can get by directly applying L2 to individual component. What I mean is, let me call this U1 up to US and this V1 up to VS. So I want to find two decomposition such that when I apply L2 on these places, I will get Vi. So if you put this extra constraints, then I want to say, oh, then maybe now you can expect some kinds of uniqueness, because this extra condition you cannot happen always in a vector space. So this being the motivation. So, and this we expect to happen to random TIs. So now let me like tell the improved framework. So here what we want is again, so your f is some t1 dot of ts. What we want is we want to decompose again. So the key being we want our operators to be like this, the combination of two operators, and then you look try to decompose such that the following happens. Right. Mm. Yeah, let me just use the following notation: li of l l2 of ti being ui and l of ti being vi. So this being u1 direction, u2 direction, us, and when you apply the operator, that is the L1 operator, you get V1 direction, V2 direction, Vs. All right. And the second thing you need is that the following thing happen is unique. This is a unique decomposition. Right. So before moving on, I just want to say that we are doing these kinds of things because there are standard machinery known for vector space decomposition in this setting. In particular, there's this algorithm by Vishwas, Chistov, and Karpinski, sometime in the 80s, which exactly does this. It does a vector space decomposition in this setting. So we'll run that algorithm in this setting, and we want it to be unique because uh, if it's not unique, you don't know what you'll get out of decomposition. It actually belongs to the original representation. All right. So these two things are important. Right. Okay. So now being the technical challenge which Raphael mentioned, how do you know that these directions will hold? There can be dependencies. How are you so sure, or why do you think it holds in the random case? So let's just try to dig further up. Let's say let's just use the sums of powers of linear forms example. Here your TIs will be just the power of linear forms, L1 to the D plus L2 to the D dot LS to the D. Here UIs will be, let's just think of uh, your L being second order partials, just as we did in the Haitian demonstration I did earlier, and your L being the first order derivative, right? So you'll get the UIs will be Li to the D minus 1, and your VIs will be Li to the D minus 2, right? For instance, now for random LIs, one can expect that their powers are linearly independent. For instance, if LIs are linearly independent, let's say S is less than N, then UIs do form a direction. Similarly, or let's say more formally, even if in the depth 3 setting, if you look at the sums of products, sorry, you look at UI will be the kth order derivative of product of a linear form, let's say Li1, Li2, Lid. So if you look at this partial derivative, it essentially boils down to some kind of linear independence condition, which boils down to some particular matrix being full rank, and that you can show that that matrix will be full rank with high probability. That is, if the matrix has not full rank, then some determinant is 0. So the non-degenerate case lie on a variety. So most likely this will not happen. In particular, in the average setting, this will not happen. And the second condition being uniqueness, that I will not go too much into detail, but the key there is the notion of adjoint algebra, which is like the main key technical part here. It's essentially so you have spaces u and v. So if you have a linear operator sending u to u and v to v, such that it commutes with the L2 operator. That is, if for every element in L2, if dou of phi is equal to psi of dou, and this happens for all the operators, this is referred to as adjoint algebra. As it turns out, it captures uniqueness, or number of times you can decompose these vector spaces almost perfectly. So it boils down that if you want to show that this condition is met, uniqueness is met, this boils down to exactly showing that this kind of weird object I defined above is trivial. That is, these two operators are nothing but scalars. So let me just make the main point that uniqueness boils down to showing that adjoint algebra, this object I defined, is trivial. Anyway, so this is the main technical challenge we overcome. This along, so basically these two things, the direction structure and adjoint algebra being trivial, are the two main obstacles. And as soon as you overtake them, you can basically get your learning result. So using this approach, let me tell what recent result we were able to show with Ankit, Neeraj, and Chandan. So we give a poly NMDS algorithm to learn generalized depth 3. By generalized depth 3 it means, so you can learn. So what's a depth 3 circuit, right? In a depth 3 circuit, think of GI being any polynomial right now. If GI is a monomial, what you get here is a depth 3 circuit. So just sums of products of linear form. But here GI can be arbitrary polynomial. For example, GI can be determinant, GI can be permanent, could be iterative matrix multiplication, or any polynomial. So you can learn this kind of things in the non-degenerate case. In particular, we show that random generalized depth circuits are non-degenerate when MD is less than square root n. Basically, that think of this, that each individual GI depend on approximately square root n many variables. And if GI belong to this family, or GI is a random polynomial, is random, then we can learn this representation. So the idea here was, since each individual GI, although G can be an extremely complicated polynomial, but it essentially depends on square root and many polynomials. So since each of these individual GI has low arity, just the simple partial derivative measure works to give us a lower bound. And the natural question was to, oh, then can we use this partial derivative linear operators to learn this seemingly monstrous circuit class? And as it turns out, all the machinery works. We can show that there is direct sum structure, the adjoint algebra is trivial if GI belongs to this families or GIs are random. And using that, the machinery I described before, we were able to get learning for this model. Okay.
Quick question. So is the relation of M and N always, it's independent, or is it always dependent?
Right. So as I said, that we need this requirement that M times D is less than equal to square root. In particular, your arity is less than square root of n. This was important in showing the direct sum condition.
No, I see, but in the theorem in the green box, right? Like, because you say polynomial, all of these parameters as if they're independent, but are they independent really, or?
No. So the algorithm means the algorithm in the box, it works if this is a non-degenerate circuit.
I see.
And it is non-degenerate if these conditions are met. So algorithm is simple. It's essentially the vector space decomposition algorithm applied to the partial derivative spaces here. But it only works when it is non-degenerate. And to show that the non-degenerate condition, so this only works in the non-degenerate, right? In the non-degenerate case, and I have not. So this, the catch is I have not written what the non-degenerate conditions are.
Right.
But they hold in this setting. So even if you, the power of these techniques are they work for extremely large top finite. So S could be some exponential, whatever. It could be n to the d to 1 by 4. You will get poly n ds m algorithm for you. This, for instance, basically these are not like constant top finite or polynomial top finite bounded approach. Pretty general. Right. Okay. Any more doubts? Okay. So this was my part on what are non-degenerate algorithms. So I gave you a simple simple example of sums of powers of linear forms, and then I just went through a bunch of meta algorithms which we use to design non-degenerate algorithms. So mostly all these algorithms follow this kind of template with these two important parts. So now I will move to the worst case template. So that's the template for worst case plan. Okay, sorry for the noise. So here the meta templates again. So I've scaled back you. So this T1, T2 up to TK again. So in worst case, we have to have some kind of very strong assumption because we are having assuming no constraint on these TIs. So the meta template is project F to a low variate setting or a low degree setting, somewhere that we can do a brute force. So I showed a brute force in the sum power sum case, right? You do some kind of variable reduction and then you set up a system solving, and then because the unknowns are constant, you can just solve it. So you try to emulate that philosophy, somehow go to a low degree or low variate setting and do kind of that thing, and then use some kind of uniqueness to learn at least one factor. So by one factor, so let's just think of these TIs as sums of products of linear forms for now. So TI being product of Lij's. You can also think of it as sums of product of sparse polynomials that will correspond to depth 4 learning. But right now, let's just look at this one. So this is the meta template. Try to get your hands on at least one of the LIs. If you get one of the LIs, then we can do something. So that's the whole. Again, there is this underlying uniqueness which pops us here as well. So let me elaborate on that. What's the uniqueness I'm talking about? So again, let me talk about multilinear depth 3 circuits. So what uniqueness comes out? So that uniqueness comes from something called rank bounds. These are well-studied object in the PIT literature. It says if you have a circuit, a depth 3 circuit, which is simple and minimal, simple being, and it computes a zero polynomial. So just a T1, T2, let's say up to T10. And if this computes zero, I will say it's simple if there is nothing, there's no common GCD among all of them. I call it minimal if nothing smaller goes to zero. Very intuitive, actually doesn't matter too much. And if that's the case, I want to say that degree of all these TIs is actually very small. So if K is less is 10 here, it's less than 10 to the power 4. So that's the rank bounds. And let's see how we get some kind of quote unquote uniqueness from these rank bounds. Suppose I give you two representations of a depth 3 circuit. Right? I give you T1 plus T2 dot dot Tk, and this somehow is also another way to write the polynomial. There's T1 prime plus T2 prime dot dot Tk prime. So I can just look at it as an identity. This is an identity. So now if I look at the minimal, so this is 0. So in particular, there would be a minimal, it could be the whole thing, but there can be, let's say, T1, T2 minus T2 prime minus Tk prime, which is also 0. So let me look at the minimal component, minus T1 prime minus Tk prime is equal to 0. What my rank bound says, okay, so since I took a minimal component that's already minimal, it says either the degree of the TIs is less than, it gives that degree of TIs is less than k to the 4, but it's not. So the original TIs I started with have degree huge. It was a degree D polynomial. So this essentially tells that there's a huge GCD among these TIs. That the simple condition has been violated and it has to have a huge GCD. This essentially says that the GCD of T1, T2, T1 prime, Tk prime has huge degree, has degree greater than D minus k to the 4. What this essentially means is if you have two representations, then in each representation, so if you look at T1, let's say, in one representation, and if you look at T1, then there exists another multiplication gate in the another representation, which has huge GCD. So if you learn one gate, you will almost learn another gate, barring only few constantly many linear forms. So this is quote unquote uniqueness that we get from this. So let's put it to use. Let's do a case study for set multilinear depth circuits. Again, doesn't matter what they say. So just assume that there is a variable partition and you have linear forms which depends on different partitions. So again, as I said, I'll do a projection to let's say k to the 10 many partitions. So D here is large, but k to the power 10 is a constant. So I'll get F projection. Okay, so let me not write the projection. It's essentially some constantly many, constantly many, constantly many. Now here also, if you focus the number of essential variables from the previous argument, since there are only constantly many linear forms here, this would be like k to the 10 here, k to the 10 here, k to the 10 here. You get, let's say 3 times k to the 10 essential variables. So again, by argument similar to previous, there's the system solving that you can set up, unknown being constantly many. You can learn f restricted to sigma. And since f restricted to sigma by brute force, you will get a representation. And since this k to the power 10 is much higher than the k to the power 4 we are talking about here in quote unquote uniqueness, it essentially gives you whatever you learn by doing your brute force. It might not be the projection of the original representation, but will have lots of overlaps. And using those overlaps, you can get your hands on, in particular, at one LIs, which is in the. So, as a conclusion to all this, what you can get is, for sure, you can get, let's say, L11. It doesn't matter which one you will at least get one linear form. You don't know which one, but you can just brute force on the representation. You can try each one of them. What to do when you know L11? You can, since these are disjoint, let's say, you can find an assignment of x1 such that this is 0. So find alpha such that L11 x1 is 0. Oh, sorry. And if you substitute this alpha, that gate vanishes. So this problem of learning for some kind of depth circuit for top n and k reduces to learning depth circuit of top n k minus 1. And you can repeat this inductively till you reach top n and 1, which is essentially straightforward by doing a black box factoring routine. So this is how you use quote unquote uniqueness and projection, the meta approach I defined. a very vague sense how we use those approach to learning. If there is any doubt, in particular in the uniqueness part, please ask me. I thought I went over a bit too quickly on that. The idea being there's this rank bounds which is like k to the 4, and if you project slightly of that, then whatever you learn will have a lot of overlap with the previous one, and that will give you sufficient information to do the reconstruction in the worst case. Okay, so
sorry,
this
so,
was
so then, yeah, so just to see if I understood, like you have the set multilinear and you're using this like minimal representation, and then you use this theorem, the structure theorem from Beer-Spielke, that they say, okay, then you don't have a lot of variables.
Right.
And then,
Right. So that variable thing actually here in the set multilinear or multilinear setting actually boils down to degree, because these are variable different. So we're talking in terms of degree, and
degree, I see.
the degree is small. Right. That's in some sense the reason why we struggle for doing non-multilinear depth 3. If you look at non-multilinear depth 3, the results are very hard to come by. There's this top 10 and 2 results by Gaurav Sinha. These are like some big 50-page papers with Sylvester Galai, and so then things get complicated, unfortunately. But so that's why in the multilinear setting, this just works because rank boils down to degree and saves us.
Oh, I see.
Right.
Okay.
Right. Okay, so this was essentially a demonstration of the meta framework that we designed. Again, it's not a cure-all. It won't work for all models, but it worked for the 2 of them, the depth 4 multilinear and depth 3 multilinear. So to conclude, let me give a clear picture how our reconstruction algorithms are placed. So the tools we have are unfortunately very limited. So oh, I see. Did I switch them? Oh, I see. This is the other way around. Never mind. So the tool that we have is vector space decomposition and some kind of brute force system solving or a brute force search over all field elements. That's the thing we do in the finite field setting. Those are the tools we have to learn. And the another important aspect that we need for these tools to work is uniqueness. And uniqueness in the non-average case comes from trivial adjoint algebra, and in the worst case comes from some kind of structural results on the zero computation of a polynomial, which come from some rank bounds or sparsity bound, which are studied in the PIT literature. So although these are very different kind of paradigms, average case and worst case, there are essentially 2 chunks. That there's this algorithm that we have, some kind of brute force or vector space decomposition, along with uniqueness that goes with it. So this is what this picture I hope connects these 2 different paradigms, and to which I like to conclude the talk. Right. And right, I can put some open questions, and also please ask any questions that you have. Right.
Okay, so thank you, Vishwas. I'll clap for everybody, but if anyone has questions, go ahead. Okay, so if there are no questions, I have one. And so one of my questions is, like, right, in a sense, I mean, of course, us algebraic complexity people or complexity people care about these questions in the worst case and average case and so on, and we want a polynomial time algorithm. But then there's all these machine learning people, and well, some theory people, you know, like David Storer, for example, right, that has all these papers of kind of tensor decomposition, which is essentially what you're talking about as well, right? So, and somehow there in their papers, like they have a bunch of constraints in the tensors that they want to decompose, and they use SOS and they use all sorts of other machinery to get polynomial time algorithms as well, right? Have you checked these papers to see if somehow their conditions are the same as yours, or is there any relation?
So the first kind of distinction between reconstruction and those applications is being our definition of reconstruction itself, because in reconstruction we allow your polynomial to be queried at any point. That actually is a very strong ask, right? In let's say tensor decomposition, we are given usually random points, things like that, right? That too usually has some kind of noise. So I think the first step back is this reconstruction ask for instance, if you give me random oracles, it will be really hard to for instance learn these kind of, for example, this approach will get much more messier. So that's one part, and the second being this um, this noise aspect of it. But for instance, if you look at generic algorithms, that's kind of has a very similar feel to the non-degenerate algorithm we have. There is, it basically boils down to you look at two slices and do some kind of vector space decomposition, and which is what happened in this case as well. So again, I to answer your question, if you Google this tensor decomposition, there will be like thousands or maybe tens of thousand paper. Which particular are you talking about? Which I like, because if you Google it, there would hundreds of them.
Yeah, I'll tell you some later then. Yeah.
Right. I hope I answered your question though. Right? There is this.
You have 2 years to answer them. I have lots of them for you. So.
Oh, I see. Good.
Cool. Okay. Any more questions?
So let me point to some open problems. So the first actually big open problem would be, so there's this, in average case, there is this general paradigm which says, oh, if you have a lower bound for a class, then maybe we can use those kinds of operators to do average case learning as well. We have some success, but things are wide open. We know lower bounds for multilinear constant depth circuits, and now with LST, we know lower bounds for constant depth circuits as well, quasi-polynomial lower bounds. So super polynomial lower bounds. So can we use those lower bounds to get non-trivial reconstruction algorithms? Unfortunately, we have not made much progress there. Right. So that is one open problem, and in worst case, I guess depth 3, top finite 3 is already very challenging.
Cool. Okay. Right. So yeah, thanks, Vishwas again. Sorry for the noise on my end. I guess there's some construction going on, but cool. Thanks very much, and yeah, thanks everybody for coming. So, bye bye.